Okay, so remember we were talking about two approaches to processing in memory, processing using memory, using the analog operational properties of memory to do computation, and then processing near memory. And we talked a lot about processing using memory to jog your memory. Essentially we're using memory to do computation, and we're still treating memory as an accelerator. And we were looking at processing using DRAM and main memory. These are slides that you've seen yesterday. It's just to bring up your cache if you're processor-centric. Okay, so we discussed how to do in DRAM bulk bitwise operations, and this was the key idea, or one of the key ideas, to do triple row activation so that you can do in DRAM majority computation, right? Okay, so I'm going to go through this relatively quickly. And then you could also do in DRAM not inversion, which gives you a functionally complete system, right? Boolean complete. Is it too loud here? No. Okay, maybe something else. Basically, which gives you a functionally complete system because now you have AND and NOT, or majority and NOT. These are functionally complete together. Which means that you should be able to express any algorithm using this bulk bitwise substrate, which is really fascinating, I think. Okay, we're going to get to even more fascinating things in my opinion. Okay, so these are the papers. This is where we stopped last time. I introduced the SIMDRAM framework, which essentially takes these majority and NOT operations in DRAM and makes them usable by anything, essentially. Whatever the programmer or the ISA designer envisions, they can express the operations using this sort of circuitry, and then we can optimize it, and then we can associate an instruction with it that when it's executed, it calls a microprogram that executes on the memory controller. And memory controller basically uses these row clone and ambit commands, triple row activation commands, to execute the instruction. And we see significant benefits out of this. Okay, but this is not the end of the story. This was 2021. More recently, this paper appeared at HPCA. This is a result of multiple years of work, including compiler development, as well as hardware development and simulation. I'll briefly describe it. I think it's really important because, as I mentioned in this course, we're going to look at changing the higher levels of the software stack plus changing the hardware. And this is a very good example of doing both at the same time. So what are we trying to do in this work? I think this is a very heavy slide, but I'll go through some of these quickly. Basically, there are multiple issues with what we've discussed earlier. One of the issues is you do bulk bitwise operations, but bulk bitwise operations can be very large, very wide, 8 kilobytes of data. But in many cases, you may not have that much parallelism, especially in irregular programs. And also, this 8 kilobytes of data is not a great granularity for compilers to target. A lot of the vectorizing compilers today target 512 bits, like AVX. And 8 kilobytes is huge compared to that. And then there's other issues like we don't have support processing using DRAM. We don't have support for reduction operations, for example, because we don't have a lot of interconnects in DRAM. We discussed that yesterday. We're going to add a little bit more interconnects. And there's a challenging programming model due to a lack of compilers, essentially. The program needs to do everything. So we wanted to fix that in this work. And in this work, we basically introduced some ideas. I'm going to mention that. And you see significantly more benefits compared to the SIMDRAM approach. Okay, so what's the problem? So this is a little bit more detail on DRAM right now. We were looking at a subarray. This is a subarray. I divide into smaller mats over here. So if you do in DRAM majority copy initialization or NOT operations, essentially you're activating multiple rows, either consecutively or concurrently. So this is a majority operation. You activate 3 rows, and everything in all of those rows get activated. So we're going to target that problem first. Essentially, it's a very wide SIMD engine, 64K bits, if you will. Depends on the DRAM design, of course, but 64K bits is very common. So this is quite large and rigid granularity, and this leads to underutilization. Because there are some workloads where you want to activate only 512. Some other workloads you may want to activate 64K if you have that much bit level parallelism. There's also limited computation support. You don't have a lot of interconnections across columns. So you can do map operations, parallel map operations, but you cannot do reduction operations easily. You have to move the data out somewhere else to do the reduction. And we want to get rid of that data movement. We want to do reduction. So we're going to do processing near memory on top of this to add some more reduction capability next to each bank. And the programming model. So we're going to look at this. So let's take a look at the programming model. The paper goes through all of these in detail, but we have a lot more to cover. So I'm going to pick the programming model over here because it's really important. In the end, to get a new hardware adopted, you really need to target the software including the programming model, including the applications. And this is what we wanted to do. So what does a programmer need to do? Even to implement a simple, or relatively simple, conditional construct like this, a programmer needs to do a lot. They need to map and align the data structures in DRAM subarrays, which is not an easy task because now the programmer needs to know what the DRAM topology looks like, right? We don't want that in general. They need to identify the array boundaries at the higher level, and they need to manually unroll the loop and map C to processing using DRAM instructions. Basically, it doesn't have to be C, of course, it could be anything that you can imagine. But they need to essentially reason about the underlying hardware very nicely so that they could actually take advantage of the underlying hardware's capabilities. Now, we did that a lot when we actually developed this hardware, but we cannot expect everyone in the world to do this. So that's why we wanted to get rid of this. And in the end, they need to orchestrate the data moment because you can do some of the operations in DRAM, some of the operations you cannot do in DRAM, so you need to orchestrate data moment as well as computation partitioning. So in the end, they need to write a program that looks like this, which is actually relatively simple in this particular case, but if the program is much more complicated, this becomes much more challenging. But what the programmer really wants to do is just write my kernel and not worry about underneath, anything happening underneath, right? So that's what we intended to do in this work, to fix some of these issues, but it's not easy to do. It's not easy to do, especially if the granularity of computation is much larger than the granularity of computation the programmer expresses in general. So what is our goal in this work? Essentially, we want to get rid of this large and rigid granularity as much as possible and design a flexible processing using DRAM system that overcomes these limitations. So how can you get rid of this large granularity? It's actually a relatively well-known idea, but it needs to be implemented. Basically, if you look at a DRAM subarray, it consists of these smaller structures called mats. So you can see that the subarray is the entire thing over here. Mat is one portion of it. I'm showing you 4 mats here. And the reason it's done this way is because if you actually have a single subarray spanning 8 kilobytes of cells, this is too long for latency. A word line, if it spans that long, it's a long interconnect, and long interconnects are bad for latency. So internally, DRAM is partitioned into mats, and mats are smaller, and the interconnects are shorter. As a result, latency is relatively low to access them. And there are reliability issues with longer interconnects, so you don't want to have very long interconnects in DRAM. So DRAM actually consists of these mats. The downside is these mats are not visible to the software or the memory controller at all, meaning that DRAM still operates at this large granularity. You cannot enable and disable mats. So the idea is to at a fine grain enable and disable these mats. This is called fine-grain DRAM. The idea is to segment the global word line across individual DRAM mats. So this is the DRAM mat as I showed you. We should be able to enable only this DRAM mat. And the DRAM mat happens to be 512 columns, 512 bits, depending on the design. We should be able to arbitrarily enable any number of these mats. And in this work, we propose this idea. We build on a lot of work that actually tried to propose this fine-grained DRAM. There's a large line of work, including one that's going to appear at HiPEAC conference from us. That makes it much more practical, in my opinion. Essentially, you segment the global word line. Whenever you activate a row, only these mats that you specify from the memory controller, which is informed by the software, are activated. And these are not activated. This is good for clearly having smaller parallelism, and also good for energy, because you're not activating things that you don't use. And the main reason why these fine-grained DRAM was proposed in the past was to reduce energy in DRAM, including a paper from NVIDIA. This is a nice paper, fine-grained DRAM by NVIDIA in 2017. They actually found out that in GPUs, activating these huge rows are very bad for energy. So they wanted to reduce the activation granularity in DRAM. Okay, so if you're interested in this topic, the sector DRAM paper is one that's coming up. It's already in TACO, yes?
I have a question concerning you're using add as an instruction, I mean for logical stuff and more and so on, I can understand what's functioning, but how you are dealing with the carry when you're adding?
So that's a very good question. We can talk later, but you need to map the data. Once you map the data nicely, carries go to the right place. Right. So this is all discussed in the SimDRAM paper that I kind of glossed over last time. You can deal with a lot of those things by vertical data alignment.
Okay.
Yeah. And I should also say that people have thought about these things in the 1960s. They designed vertical processing engines, but none of these ideas carried over because people, a lot of the data layout in modern systems is horizontal as opposed to vertical. So each bit needs to be aligned nicely. Okay, so that's the idea basically. The key idea is to use fine-grained DRAM. This improves SIMD utilization. For a single processing using DRAM operation, you only access the DRAM mats that contain the target data. And now you have another opportunity, which means that while you're executing one instruction that's targeting these mats, you can execute another instruction targeting some other mats. So you could actually pack multiple instructions together, either in VLIW mode or even more loosely, a multiple instruction, multiple data mode. That's why it's called multiple instruction, multiple data execution model in DRAM. So these could be belonging to different applications. Different applications can be executing in different mats. And we have a method for scheduling this, both in the software as well as the hardware. Okay, this is something that I'm not going to talk about, but we also found out that it's very bad to not have reduction operations in DRAM. Unfortunately, there's no easy way of implementing reduction. So you did some, let's say, bitwise addition, and then you want to add the results of those additions. Now, if you want to do that, you need some reduction primitive. You need to move the data from here to some other match, for example. So we add some interconnects to enable that data movement. It's relatively low cost, but this is processing near data now. It's not using the operational properties. We're adding more stuff, logic, to do this. But it's important. And then easing the programmability. Let's talk about this. This is important, as I said. Basically now, because we're targeting only mats or groups of mats, the granularity that we can target at the compiler can be relatively small, 512 bits. And 512 bits is what vectorizing compilers target today when they actually vectorize code for AVX architectures, for example, existing SIMD architectures. So what did we want to do with the compiler support? Essentially, we want it to be transparent to the programmer as much as possible. We want to extract SIMD parallelism from an application and schedule processing using DRAM instructions to maximize the utilization of the DRAM. And we add 3 LLVM. Geraldo did a lot of work to add 3 LLVM-based passes. One is to identify code that can be vectorized. This could be eased, of course, if the programmer writes vectorized code to begin with. And the second is scheduling the code and map the data. And the third is the generation of the code. I'm not going to go through the details in general. The paper has a lot more details, and we will open source the code for the compiler. We already open sourced the code for everything else in this paper, but the compiler is still not fully open sourced. So the code identification identifies SIMD parallelism, generates these instructions, processing using DRAM instructions, and sets the appropriate vectorization factor. It can say basically 1 mat, or 2 mats, or 10 mats, or 20 mats, depending on the vectorization in the code. And then it distributes the independent processing using DRAM instructions across DRAM mats. This requires not just code scheduling, but it also requires the mapping of the data to the appropriate maps, to the appropriate mats in DRAM. And finally, code generation is easy after you do that, I think. You basically translate this data flow graph into instructions. Okay, I went through a lot of things very quickly, but we have a lot more to cover. But this is really important. That's why this paper is actually a result of multiple years of work. And there's a lot more to do, actually. If you're interested, we discuss a lot of other things. I'm going to get back to some of these later on. The instruction set architecture support, data transposition support, because sometimes you may want to operate data in a vertical manner. Each bit is in different rows. But sometimes the consecutive bits in a data structure should be in consecutive locations horizontally. And in order to be able to operate on data in these different modes, you need to actually transpose the data. And we add transposition units in hardware to do that. This was actually added in SIMD before. We just carried over. So data coherence and address translation are actually important topics that we're going to discuss in adoption. And then there are other things that I'm not going to talk about here. So let's take a look at the results a little bit. So you can download all of this code from our GitHub and actually run some of these simulations. You can actually add your own benchmarks, etc. In the end, we see significant energy efficiency improvements compared to GPUs and SIMD-RAM. So I've already given you the SIMD-RAM results yesterday, so we improve upon that significantly. This is like compared to SIMD-RAM, we get 14x improvement. In this case, we optimize the GPU quite a bit, so GPU actually seems to perform better than SIMD-RAM, but we still get significant energy efficiency over GPUs. And the main reason is we can actually get a lot more efficiency in DRAM. Plus, compared to CMDRAM, we can actually do, we're actually using workloads that don't have that much parallelism, and it can actually reduce the energy cost of activating huge rows. Okay, I don't want to spend too much time on results, but performance also improves. And if these results are actually not even taking advantage of a lot of banks. If you do this across many, many banks in DRAM, you get a lot better performance and a lot better energy improvements. And these are some of the results over here. So this clearly comes at an area cost, because now we add area cost to segment the word lines and also add interconnects to do the reduction. You also need area cost on the CPU die, because the memory controller really orchestrates which mats are activated based on software instructions. But I like this because it's really software now is telling what part of the DRAM you should really activate and work on. Okay, so this is the summary, but I'm going to skip that. Any questions on this? Okay, so I wanted to go into this a little bit more because this is, in my opinion, this sort of stack, across the stack design is really important. We have several other works on PIM programmability. I'm going to mention some of these later on, but just to give you an idea, we actually worked with NVIDIA a while ago to do offloading from GPUs. So you have a main GPU, you offload computation, some of the warps that are quite memory intensive to GPUs that are near memory, and then we wanted to do this completely transparently to the programmer. This is not processing using memory, this is processing near memory. I'm going to talk about that later on. We have some other works that take advantage of data parallel constructs to do better in processing in memory. Another work that I will mention later on, this is mainly targeted to the UpMem system. All of these are interesting. They could be targetable for processing using memory and near memory as well. Another work that's relatively old, I may mention it if we have time later on. Okay, if there are no questions, I should say that, okay, these are very interesting, and some people, reviewers for example, always criticize saying that, oh, this is not real, come back to us with the real stuff. I will say that that's not a good criticism. That's basically a criticism, but if everybody has to do something on real systems, then there will be no progress in the world. So we should really imagine future systems. Now that said, we also did some work to see, can you actually do some of these operations on real DRAM chips? And this is the real fascinating part for me. Basically, real DRAM chips are already quite capable. I showed you earlier that they can perform row clone, right? They can actually do row copy operations, row initialization operations with almost 100% success rate, reliability, 99.99 actually. I'll show you some more on that one. But can we actually do these arithmetic logic operations like AND, OR, and majority, and not in real DRAM chips? And we resorted to our DRAM infrastructure. This is the infrastructure that I introduced in an earlier lecture. We're going to see it even more in the RowHammer lectures tomorrow and later. But we use this infrastructure. It's essentially a soft memory controller. Just to jog your memory again, you can program the memory controller to change the timing parameters between different DRAM activation, pre-charge, etc. operations. And this is the latest version. If you're interested, people are using it for various things. We'd be happy to support it. And in these works that have appeared this year, all of them appeared this year, we basically demonstrate that commercial off-the-shelf DRAM chips, without any modification to DRAM, can simultaneously activate many rows in the same subarray as well as different subarrays. You can perform NOT operation, so you can actually get the NOT inversion in real DRAM chips by violating the timing parameters. I'm going to give you the principle, so we're going to go back to the very low analog circuit levels right now. And you can actually perform essentially everything that we envisioned. In slightly different ways, but we envisioned that. So basically you can do AND, NAND, OR, and NOR operations, 16 input ones. So we were not envisioning 16 input ones in our earlier results, if you remember. Now you can do 16 input AND operation, which basically can do nice, if you have a lot of data parallelism, you can exploit that. So let me give you some of the basic ideas. So we are able to activate multiple rows in the same subarray, but we also found out that you can actually activate multiple rows on neighboring subarrays. So this is subarray X, this is subarray Y. They normally share sense amplifiers. That's the DRAM design. Because sense amplifiers are expensive in DRAM, DRAM manufacturers minimize the number of sense amplifiers in their design. Just to give you an idea, a sense amplifier, the size of a sense amplifier is 100 to 200 times the size of a DRAM cell today. So they want to get rid of the sense amplifiers as much as possible, but they cannot get rid of all of them because this is needed for correct operation, right? To sense the data. So that's why neighboring subarrays share sense amplifiers. Now this is a normal sequence of operation. If you want to read from row A, you activate row A, and then you can pre-charge row A after some time, dictated by DRAM standards, and then you activate row B. This is how you would normally operate. Now if you reduce the timing parameters greatly by having a programmable memory controller like we designed, it turns out you can activate both of these rows, because you activate this row, before the row gets settled, you activate this row, so both rows stay activated. Now this means that they can communicate through these shared sense amplifiers. Now let's take a look at those shared sense amplifiers. As I said, I'm going to go below to the lower level. How do you get the NOT operation? Essentially, this is the source row in the subarray X at the top. This is our destination row. And this is a NOT gate clearly. So you should be able to get the NOT of a source into the destination. Basically, the idea is to connect rows and neighboring subarrays through a NOT gate by simultaneously activating these two rows. So you violate the timing parameter. When we violate the timing parameter, the next row gets activated as well, which means that the data that you sensed, which is A bar, goes into the destination. So that's the basic idea, very simple. When you activate the source row, you sense the data and the inversion, and when you activate the destination row, it gets the data that you've sensed. Makes sense, right? So it's a NOT gate essentially, and this was not known before, which is important for clearly. NOT is important. We were able to do AND and OR, but NOT is necessary for Boolean completeness. Okay, how do you do that? So you can generalize this idea actually. You can manipulate the bit line voltage to express a wide variety of functions using multiple reactivation in neighboring subarrays. Let's take a look at that. So I'm going to generalize this. This could be generalized to more than 2 rows also. I'm showing you 1 bit per row, but let's take a look at the 2 case. So this is the subarray X at top. This is subarray Y at the bottom. Well, Y is not a good thing, but the second subarray, let's say. Now if you do multiple row activation, what happens is you activate these concurrently and you activate these concurrently. Now when you activate these concurrently, the bit line voltage is really a function of, or average of, voltage in A and voltage B. And the bit line voltage here is really an average of voltage X and voltage Y. And the sense amplifier really compares the voltage over here to the voltage over here to do the sensing. Now if you carefully place some data to A and B, you can actually do computation function on X and Y. So let's take a look at how do you do AND and NAND. Okay, so I'm going to call the top subarray the reference subarray. I'm going to manipulate the voltages there carefully, and there are ways of doing that. And then at the bottom, the compute subarray. These are the inputs essentially. Okay, so initially I'm going to put VDD to one of these and VDD over to one of these. And you can do that. There are prior works that show how to do that. And I'm going to violate the timing parameters. Now what will happen is at the top I'll get the average of VDD and VDD over 2, which is 3 VDD over 4. And at the bottom I'll get the average of X and Y. Now it all depends on what X and Y are. The result of the function that I get in the reference and the compute are going to be the comparison of VDD, 3 VDD over 4 over here with the average of X and Y. Now let's take a look at what X and Y could be. So assuming VDD is 1 and ground is 0, X and Y is, if you want to, if the inputs are 0, 0, what will happen over here is, at the bottom you will get, sorry, something is happening. Yeah, at the bottom you will get 0 over here. Oh. So, yeah, at the bottom you will get 0, which is ground, and at the top you'll get 3 VDD over 4, and the sense amplifier will compare them and amplify the result. Amplification means that this goes up to VDD and this goes up to ground. So at the compute subarray you'll get 0, which is the compute subarray, and at the reference subarray you'll get 1. Okay, so this is true if X and Y are 0 and 1, because over here you get VDD over 2 averaged, and it's still lower than 3 VDD over 4, so we'll get 0 and 1 over here. This is true for 1 and 0 also, because it's just the same thing, symmetric. Now the interesting case is 1 and 1. When this is 1 and 1, these are both VDD, and this is 3D VDD over 4, which means that when the sense amplifier compares that, the result in the compute subarray will be amplified to VDD, higher voltage, so you get 1 over there, and the result in the reference subarray will be amplified to 0, so you get 0. Now let's take a look at what function we got actually. The function we got in the compute subarray is really an AND of X and Y, and the function we got in the reference subarray is really an AND of X and Y. So this sounds interesting, right? Yeah, I went to a little bit lower level than maybe some of you are comfortable with, but this is how an analog circuit really operates. And it's not just an analog circuit. That's the beauty of DRAM. There's a sense amplifier, which is analog to digital converter. So this is not pure analog computation. This is really analog computation immediately translated into digital. So DRAM is also designed to be quite stable for that purpose. So we're not doing computation in the analog domain for a long time. It's a very short time, if you will. So this is beautiful, and then you can convince yourself by doing this that you can get NOR and OR operations as well by carefully manipulating the voltages. So this is fun, I think. Basically, you can actually express AND, NAND, OR, and NOR. You can find more in the paper. Now let's take a look at, this is theory. Is this theory realizable in real DRAM chips, off-the-shelf DRAM chips? So that's where we go to our infrastructure. We test a bunch of modules from different manufacturers. And you can tell me, you can ask me why some manufacturers are not there. I'll be happy to answer. Basically, this is what we see. This is the number of input operands, 2, 4, 8, 16. And these are different operations, AND, NAND, OR, NOR. And this is success rate. The definition of the success rate is in the paper, but it's really a reliability metric. And you can see that the success rate is usually quite high, even though DRAM chips are not designed to do this, right? When you buy DRAM, nobody tells you, oh, you can do computation in it. You can do read and write. You're not even supposed to violate the timing parameters, right? We're doing something that is not, that you're not supposed to do. But our goal is to show that these DRAM chips, even though they're not designed with this in mind, they're not optimized for this purpose, they're capable of doing these operations that are really envisioned based on theory. And that's the idea, basically. You can actually see these operations in real DRAM chips, which is fascinating. And my student Ismail actually went on and used these operations. Right now we're using these operations to actually implement full applications like neural networks in real DRAM chips. It's not perfect, but yeah.
This graph, does it show repeatability in the same DRAM or variability over multiple DRAMs at the same time?
So it's both, basically. So essentially it's both. It's really showing repeatability. We repeat the experiments many times, but we also test many DRAM chips. The graph is a little bit more complicated. Yeah, but we have the graphs for every single DRAM chip as well. Yes?
What do you mean with high success rate? 94%.
So 94, what is the highest success rate? Essentially, 6% of the bits don't work as expected. So you have some errors.
Okay.
Yeah.
Lot of faults.
Yeah, exactly. But that's expected because DRAM is not designed for this purpose. The fact that we get even 90% success rate is quite good in my opinion. Okay. And then data pattern changes these effects. We're going to talk about data pattern tomorrow, but this is the NOR operation. So it depends on the data pattern. You get slightly different success rate, but not that bad. And the impact is consistent across different types of operations also. There's a lot more analysis in the paper that I'm not going to cover over here. But essentially, we also test temperature, speed rates, chip density, die revision, etc. And you can certainly find more in the paper. Okay, so I think this is not to say that you should take off-the-shelf DRAM, violate the timing parameters, and do your computation. You could do that. If you actually, all of these are open sourced. You can take our open source system. You can take an FPGA. You can use our DRAM vendor and use the source code we provided and tie it to an application. And you can actually take an application and execute in off-the-shelf DRAM chips. If you're successful, that's great. We'd be happy to help with that. But the real reason why we actually did this research was to demonstrate that there is real computation capability. DRAM is really a computation substrate in addition to a memory substrate, and there's a promising potential there. We should really go and design DRAM to maximize the success rate of these operations and to make sure that they actually work fully correctly. And I think that's possible. Okay, I will mention one more work that actually goes even deeper to look at the reliability of these operations. I'm not going to talk about everything. Again, in this work we test a lot of chips and we show that they can perform 9 input majority operations, for example. For example, you can activate up to 32 rows, and up to 32 rows you can have 9 input majority operations, and you can replicate that 3 times. 9 times 3 is 27, right? So you can actually improve the reliability by replicating the number of operations that you're doing. This is really redundancy in the operation space. I'm not going to talk about that. I'm going to talk about something else over here. So these are some of the results in the paper. You can increase the robustness of these. I'm going to talk about something even simpler, which is copying. We're going to get back to copying. So remember row clone. Yesterday I showed you that you could actually copy a source row to a destination row by doing 2 consecutive activations, which is great. That's 1 row only. In this work, we show that you could actually do it to many rows. You could copy a source row, and if you do multiple row activation, many row activation, that source row can get copied to 31 other rows. Now, why is this interesting? This is actually a very fast way of initializing DRAM. And a very fast way of initializing DRAM has many applications, as we've seen yesterday, security being one of them. Actually, there are multiple aspects of security. One aspect of security is to prevent from cold boot attacks. So some people actually, if they have physical access to your DRAM, they take it, they make it cold so that it can keep the data for a long time, and they read whatever data is there. So if you can actually initialize your DRAM very quickly, if you detect this sort of thing, you can actually get rid of the private data that you don't want to expose to anyone. And we show in this work that this is actually a very good protection for cold boot attacks, better than existing mechanisms. And it's a lightweight protection. You can of course do encryption, but encryption is a very heavyweight protection for those things, especially in IoT or edge type of systems. Okay, so I think I already said all of these. You can actually copy one DRAM row to many rows at very high success rates. I'm going to show you the success rates over here. And this is very resilient to data pattern, temperature, and word line voltage. So you can see the success rates. This is actually almost 100% in many cases. There's some variation across chips, etc. So copying is very easy because it doesn't involve any computation, so the variation in noise is not that much in this case. And then data pattern, once you go to 31 rows, it's still, you can see the numbers over here are all greater than 99%. Okay, the paper has a lot more analysis on temperature and voltage. These are important things to examine, and these seem to be highly resilient to that. And there's a lot of other stuff in the paper. Since I don't have time to talk about it, but why is this working this way? Well, it's because of the row decoder circuitry. The way the row decoder circuitry, the logic works is, whenever you activate something, some other parts of the row decoder circuitry also gets activated, and if you don't give enough time for the circuit to settle, basically you're really activating a row in somewhere else. And this is really a function of the addresses and the bits that you have. But we have a row decoder circuitry in the paper. And there are a lot more results that I'm not going to talk about, since our goal is not to cover this paper in this course. And this is also open source and artifact evaluated. You can download it. You can actually start doing research. We'd be happy to help. Again, this may take time to get into research here because you need to modify the FPGA, well, using our code, and you may need to do other interesting things, but we'd be happy to help. Yes?
Yeah, you had this multi-row copy.
Yes.
In the DRAM here. And that could be interesting for parallel computing, of course.
Yes.
Is it anything that should stop you from doing that SRAM also?
Yeah, so that's a very good question. What about other technologies like SRAM? I don't believe so. I think a lot of these ideas that we've described are applicable to other technologies also. Yes. Okay. But we have not demonstrated in SRAM, but I believe people who are working on SRAM can demonstrate it. Actually, I should take that back. Other people have demonstrated in SRAM that you could do this sort of bit line based computation. Yeah. But copy, I don't know if people have really analyzed it as much. Excellent question, because next I'm going to talk about some other technologies soon. Okay, yes?
What's the efforts to overcome the 6% failure rate?
Yeah, that's a great question. That's research. That's what we're working on right now.
But is it worth it?
It's worth it, I think. Well, the 6% you said, right? The 94. I think it's worth it, yes. So I think there are two answers to that question. One is there are some applications that could actually tolerate this. Yes. I don't think that's the best way. In the end, not all the world is approximate. But I think the effort to overcome that is changing the sense amplifier and changing the row decoder such that they're more robust in the way we're doing things. Right now, truly DRAM is not designed for this purpose, right? We're really violating the timing parameters so that we get a good timing to show these operations. Even these operations that we showed are not based on the perfect timings, right? If we actually do a complete sweep on the timing, we should be able to come up with a better operating point. But our resources are not enough for that. All of these tests actually take months and months of time. So even our results are conservative in that sense. I believe real success rates are really higher if you find a better operating point. And if you actually know how the sense amplifier and the row decoder are designed, you can actually do much better. Okay, before going into other technologies, I'm going to talk about what else can you do using DRAM. This is actually also fascinating. These are some earlier works we published in 2019. Again, these are based on real DRAM chips using our infrastructures, where we show that so you access DRAM, you have some latency. I don't have slides on this. You have some latency. Essentially, normally you use some latencies that are required by the manufacturers. What if you reduce that latency? If you reduce that latency, at some point a cell fails. Now it turns out some cells always fail, some cells almost never fail, and some cells fail randomly. If you come up with some latency to access DRAM, some cells sometimes fail, sometimes don't fail. Which means that if you repeatedly keep accessing those cells, you'll get a random number generator. And we believe this is true random number because it's really based on the sense amplifier noise. That's a physical process. And we show in this work that you can actually generate true random numbers at high throughput, low energy using DRAM. So you don't need to have another random number generator circuit, but you just use DRAM, violate the timing parameters, and the result of the bit gives you a random number. This is fascinating. So later we actually showed that you could actually do this in a better way by activating multiple rows. And we actually saw some other works on this topic. But I'm not going to talk about that, we don't have time. But essentially you can generate random numbers in DRAM. So why is this interesting? Because if you actually want to push computation on the memory side, I believe one of the biggest, one of the important advantages is to push security critical computation. Because one of the issues we have in hardware security today is you move data a lot. Once you move data a lot, data gets exposed to potential attackers, like side channels. But if you actually keep the data in DRAM and do the security critical functions in DRAM, and if you want to do a security critical function, you usually need a random number generator for encryption, etc. Then actually I think you can get to a better, much more secure system. Now this is something we're working on right now, and when we talk, maybe tomorrow we'll talk about that a little bit. Okay, you can also do physical unclonable functions in DRAM. So those cells, when you violate the timing parameters, as I said, some cells never fail, some cells always fail. Now if you look at the always failing cells, this is very unique to the DRAM device. So in DRAM device 1, some cells fail. In DRAM device 2, some other cells fail. In DRAM device 3, some other cells fail. Meaning that you have a signature of the device. And this is a physical unclonable function, which is really used for attestation functions in security. And this is also very interesting. Okay, I don't have time, but if you want to implement more sophisticated functions, you can do it using lookup tables in DRAM. One of the downsides of the prior works that we discussed is they're based on very simple primitives, AND, OR, NOT, NAND. These are very simple primitives, right? But if you want to do a multiplication immediately, for example, in those works you need to do it serially. It takes time to do a multiplication. That's why the previous works are a very good fit for actually low bit width execution. Yes?
One slide back.
Oh, one slide back, okay, yeah.
Yeah. I mean, in industry we are very interested in that no one is tampering with our product, like changing a component.
Yes, this is good for that.
Could you use it for that, to checking that the DRAM has not been exchanged to something that...
Exactly, exactly, yes. That's one of the functions of physical unclonable functions, and we showed that you could use it for that.
Okay.
Yeah. Sure. Okay, so lookup tables, you can actually do multiplication, division, for example, although this requires some more changes to DRAM that I'm not going to talk about. But I believe it's really important to examine things like this going into the future. How can we implement more complicated functions in relatively simple ways? Here, you don't need to add logic to do multiplication. Adding multiplication logic is expensive, although we'll get back to that with near memory computation, but you could do it with lookup tables. Okay, what about other types of memories? This already got started. I'm not going to talk about SRAM. A lot of these have been shown in SRAM also. I think SRAM is quite interesting, no question about that. But in the end, it's not very scalable to very large data sets. But we should be doing all of these in SRAM also. I'm going to talk about flash. So SSDs a little bit. SSDs are actually quite important because we have a lot more data in SSDs. And we've essentially shown that you could do very similar things in SSDs. Very quickly, this is a paper at Micro. Essentially, you could do computation on multiple operands with a single sensing operation. And you get very accurate computation results because in SSDs you can have a memory controller that you can modify easily. In DRAM, unfortunately, you have to violate the timing parameters. With SSDs, you have a lot more flexibility because the flash controller is something that you design based on the SSD. Right? Okay, based on the flash chips. So this is what we're going to do. Essentially, we're going to do multiple row activation again. And when you do multiple row activation, you get the bitwise AND of all of these operands. Essentially, it's block bitwise execution again. So why does this work? Very quickly, without going into a whole lot of detail, once you simultaneously activate multiple word lines, multiple rows, you get the bitwise AND. And the reason is a bit line reads as 1 when only when all of the target cells store 1, because that's when the current is conducted. If one of these cells stores 0, it's an open circuit, which means that you get a 0 in the output. All of these cells should be really 1 so that the circuit is closed. And that's the basic operation of NAND, because this is why it's called a NAND string. You have a string, and on that string hangs a lot of floating gates. And if all of the floating gates are charged, or set, if you will, or 1, then that string is complete, meaning that it's a closed circuit. Okay, so this is how you get an AND operation. And this actually happens with a single sensing operation, which is really fast in Flash. How do you get the OR operation? Now, if you look at multiple word lines in different blocks, so Flash consists of different blocks. We looked at a single block in the previous case to get the AND operation. If you look at different blocks, they are connected to each other via something like an OR, or wired OR, if you will. So if any of these is a 0, if any of these is a 1, you get a 1 at the end. All of these things that are connected to that wired OR need to be a 0 so that you get a 0 at the end. And this is an OR function in the end. Okay, so that's how you get the OR function. And Flash is actually nice because in Flash you normally have not and not easily because there's an inverse read function in Flash. If you're familiar with SSDs, you don't only get the page itself but also the complement of the page. This is what Flash provides you nicely off the box, so you don't need to worry about implementing not in a different way. So in this work we showed that you could do these reliably, and to make sure you do this reliably, you need to change the Flash programming a little bit. We eliminate all the row bit errors. We tested a lot of Flash chips in this particular case. I don't have the picture of the infrastructure today, but I'll show you in the RowHammer lectures probably. And we basically do single bits per cell computation. We trade storage density for reliable computation a little bit. And we do more precise programming, meaning that in Flash, when you actually encode data, you encode data in voltages. And you have a voltage range, and you could actually program longer so that you get the voltage range to be tighter. And that's what we do in this case, and that's what the Flash controller does. It takes a little bit longer, about 10% higher latency, less than 10% as you can see over here, but it gives you the computation capability. And you don't need to do this in places where you don't need to do computation. So again, you can do this with no changes to the cell array of commodity DRAM chips. You can have many operands, and you can have, essentially, we didn't observe any bit errors in the tested Flash cells. This is very different from DRAM. In DRAM, we cannot do this, unfortunately. We don't have the capability to manipulate charge in cells as much as we have the ability to do that through a Flash controller in Flash. Okay, and the results are pretty good actually. These are simulation results based on what we have seen, and we see significant energy and performance benefits. And the energy and performance benefits actually increase with the number of operands that you're using in these operations. Okay, I'm going through some of these quickly because I think the basic ideas are very similar. And other people have actually shown that you could do similar operations like row clone and bulk bitwise operations in phase change memory and other non-volatile memories. I'm not going to go through this, but essentially the idea is the same. They were inspired by our work that was published a year before. This is a beautiful paper that also talks about how to do it in non-volatile memories. I will mention emerging memory technologies a little bit because I think it's important to think about them, as I mentioned earlier. Basically, emerging memory technologies have some other capabilities that I believe DRAM and Flash are not capable of, which is matrix vector multiplication in the analog domain. And the reason is they have this crossbar array structure, which I'm going to show. They can basically operate on multiple pieces of data, again using analog computation rules, using Kirchhoff's laws. And the main principle is bit line current that you will get is a sum of products of the word line voltage times the cell conductance, or 1 over resistance of the cell. Okay, let me show you a picture. So basically this is what you see in an emerging technology. It's a crossbar array. You can store your weights in each of these places over here, and your input can be whatever you want to multiply your weights with. It's an input vector, and the result will be the matrix vector multiplication using those weights. So why does this work? Essentially Kirchhoff's laws. How many people know about Kirchhoff's laws here? If you remember from your high school physics or something. But it's very basic. You have the input voltage, and then you have the conductance, which is 1 over resistance over here. the current that you get in the bit line is the sum of current over here, and the sum of the current contribution that comes from here and that comes from here. In this case, it's I1 plus I2, and I1 is voltage times conductance over here and voltage times conductance over here. And you can actually generalize this over here, so you basically have a vector multiply with this column over here, and then the result is over here. Let me actually animate it very quickly. So these are the resistances that you have. This current over here is the dot product of the voltages over here and the resistances over here. And that's true for, well, that's the equation that we probably know. And that's true for all of the other bit line currents over here. And once you do this sort of computation, you store your weights inside the matrix, and then you supply the inputs as voltages, and then hopefully you'll get the good outputs. That's the idea. Now, of course, in this case, you need to encode your values nicely. And you need to make sure that this analog computation happens reliably. This is a bit harder. There's a lot of work in this area to make this reliable. As the sizes of your array grows, it becomes harder and harder to make it more reliable. Yes?
How do you affect the silicon process and your manufacturing view? You have like resistors, you probably don't have any high looping level.
Yeah.
You can give you exact resistors.
Yeah, so basically how do you deal with variation? That's the question, I think, right? Yes, that's a problem with all of these technologies. That's a problem with DRAM also, actually. But that's a problem with these technologies even more because you're really doing the computation purely in the analog domain. Yeah, you need to somehow quantize and work with ranges, etc. There's a lot of work in this area that I'm not going to go into. But I think people should really keep pushing this area also, no question about that. And these are some of the papers that have been published. So the interesting thing is, I should say, this processing using memory. This is an example of processing using memory in my terminology, right? You're really using the analog operational principles of the memory circuitry, just like we were doing with DRAM. The interesting thing is this was discovered in the early 2010s or so. A lot of the papers were on processing near memory, which we're going to switch to soon. But in 2010s, these may not be the earliest works. Also our works, our first work on this topic was around 2013 after one rejection. Let's say it could have been 2012. But essentially, these ideas were all discovered in early 2010s, unless I'm missing something that I have no idea about. Please correct me if you find something. And that's fascinating to me, because analog computing has been known for a long time, but using memories to do analog computation is something that that people have been looking at much more recently compared to the past. And I think my feeling for the reason for this, of course I cannot know, right? But it's because people have thought of memory as memory. This is memory, we don't do computation in it, let's just design it as memory, right? People have not thought as memory as something that can fundamentally do computation as well. And more recently people have started thinking that way, and I think this is a really good change in the right direction. We should not think of something as doing only one thing, perhaps. Okay, and that brings me to processing near memory, which is, as I said yesterday, easier to do. That's why a lot of industry prototypes today are processing near memory prototypes. But in the end, it's less efficient, although you will see very good results with this also. But in the end, if you really want to get highest efficiency, you should push the computation inside the memory circuitry as much as possible. Does that sound good? Should we switch? For those of you bored with processing using memory, maybe. Okay, this is going to be, I think, a little bit higher level, in the sense that you're not going to see analog currents, etc. You'll see more applications. How can we take advantage of putting logic near memory for different applications? What kind of logic do we put, etc. Those are the questions that start being asked. And where do you put the logic? It becomes a question. And we have a lot to cover in our long paper. I don't have time to cover everything, but I'm going to pick and choose. And we're going to still treat memory as an accelerator. We're not going to go to this distributed computing paradigm, which is very interesting going into the future. I'm going to give you some things that I believe are very interesting. So when we started this work, we wanted to look at graph analytics, because graph analytics is a very interesting application. You have huge data sets. And clearly these numbers are outdated over here. And if you want to have higher performance, putting more cores to the problem doesn't help that much. Essentially, this is real results from some of these data sets. You get very little speed up by increasing the cores by 4x, for example. And that's terrible for efficiency also. Energy efficiency is also bad. And the main reason is, this is a very famous PageRank type of algorithm. You get frequent random accesses. Not everything is random. There's locality. There's locality at the like larger granularity, but at the smaller granularity, a lot of things may be random. And you have very little amount of computation on the data. You just do some updates on a graph node, and then move to another graph node, and then move to another graph node, and then move to another graph node. So this is really not good for the way we move the computation, right? You don't have that much locality to exploit. So when we first started doing the research, we were very interested in 3D stacked memories, and we believed, and I still believe, 3D stacked memories are a good substrate for doing computation. Here you have a logic layer, and then underneath, on top of that, you have many memory layers. HBM is one example, high bandwidth memory. It's used as 2.5D stacked memory today, but going forward, there's no reason why it cannot be completely 3D stacked. And I think going forward, actually, it's going to happen in HBM4, for example. They're going to have a true logic layer underneath memory layers. And the true logic layer, there will be a lot of opportunity for doing computation. But basically, what you can do here is, because of manufacturing, 3D manufacturing technology, you have through silicon vias, which are not the best way of connecting through the stacks. There are better ways of doing it, using monolithic 3D fabrication, for example, but that's future. We're not even talking about that in this work. In the logic layer, you can put any kind of computation. That's our assumption. There will be some industry people who will tell you that, oh, you cannot do that. That's because their logic layer is not good today. They can make it better, and they're going to make it better. 5 years down the road, if they don't make it better in HBM4, come and tell me that I was wrong. I'm happy to be wrong. But I think they can make it better. Essentially, in the logic layer, you can do anything in logic, limited by the thermal limits, because now you have logic and memory stacked on top of each other. Logic has high bandwidth, low latency, low energy connections, but then if heat is generated, heat has nowhere to escape, right? Because you're really covering everything with some memory and logic in the end. So this is a fundamental problem with 3D stacked memory, is that doesn't help them to scale to a huge number of layers, but we can talk about that separately. So okay, basically we're going to do computation in the logic layer. This is a huge system design paper, and the idea is, in the logic layer we're going to divide into what's called vaults, and these vaults have DRAM controllers and also a simple in-order core to do computation. It's actually a very general purpose system, although we use it for graph processing. You could use it for machine learning as well. We may get back to that. In each vault controls and owns the memory stack on top of it. Now these vaults, these cores are connected to each other through some network. And then you have this 3D cube. This is one cube, if you will. And then we connect many of these cubes together through some interconnect, so that we can actually scale up the system to a very large memory and compute capabilities. So if you think about this, this is really a distributed system over here. And we attach it to a host processor. Host processor offloads computation, just like a GPU. It offloads computation, and the computation is graph computation in this case. And the programmer programs everything over here. There's no virtual memory. There is no coherence over here. Everything is physically addressed. So we're going to program it using message passing or remote procedure calls, as you will see. So we basically changed hardware as well as the programming model in this particular case. So what do? Essentially, we partition the graph across these cubes. Hopefully you have a good graph partitioning mechanism. We evaluate that in the paper. I'm not going to talk about that. And then partition the graph across these vaults within a cube as well. And whenever we want to update a graph node, we don't move the data to the place that wants to do the update. We move the function to the data that's going to be updated. So you basically move functions around as opposed to moving data around. There could be a better way of balancing those. Sometimes you may want to move the data around, but we don't do that. We're actually quite rigid about moving functions to update the data. I'm going to show you an example of that very soon. So basically we do communications via remote function calls across these processors. So there's a message queue, for example. It's a messaging system. So let's take a look at an example. This is how you update the next rank in PageRank. This update on vault 2, for example. Oh, sorry. This is how you would actually do the function call. You basically use a remote function call called put, and you basically send the rank over here. So you basically put over here, as you can see, and we basically send the input data to the other vault that houses the data that's going to be updated. Again, I'm going through this relatively quickly, but the basic idea is very simple. Send the function to the data that's going to be updated. That's it. And it requires some changes to the programming model. As you can see, we use get and put functions. But if you're familiar with message passing, this is really message passing in the end, right? Okay, so we also add some prefetching mechanism. It turns out these in-order cores these in-order cores over here have access to huge amounts of bandwidth, and we cannot saturate that bandwidth just by using programming, at least the way we program the graph applications. So we add a lot of prefetching mechanisms that I'm not going to talk about over here. So let's take a look at some results. There's a lot that is missing in this description because I want to move to other works also, this relatively old work. But this is actually an important work that shows the benefits of doing 3D stacked memory based in-memory computation. At the time, we started this work in 2012. The paper was rejected 2 times before it got into ISCA. So if you have paper rejections, don't worry. I have my own list of paper rejections and I can talk to you about that. But it was not rejected for good reasons. But in the end, it appeared at ISCA, and it, I think, inspired a lot of work. So at the time, in 2012 or so, these were the systems that we had. Essentially, these are all processor-centric systems. You can see the processor has access to a small amount of bandwidth. Even with hybrid memory cube, which was a 3D stacked memory of the time, you get small amount of bandwidth because you're pin limited, right? Tesseract doesn't look like any of those systems. In Tesseract, compute and memory are coupled. Essentially, each of these boxes is a cube, and then we basically have a distributed system of cubes, which is a different way of thinking about the system, right? This way, I think there are many benefits. We wrote a retrospective paper on this topic, but one of the benefits is really you're scaling the computation capability with the memory capability at the same time. We call this performance capacity provisioning. So basically, as you increase the memory capability, your computation capability also increases. That's not the case in this sort of traditional systems in general. Okay. And you can see that the number is pretty high, 8 terabytes per second access. So these 512 small cores have 8 terabytes per second access to memory, which is actually, if you follow the numbers in some of the keynotes, etc., this is actually better than in some of those numbers today. Although with HBM, things are getting much better. Okay, so what is the end? In the end, we ported and programmed 5 different graph processing algorithms, and we saw significant performance improvements. It's about 13x compared to the baseline systems, as you can see over here. So one of the reasons is because we can use a lot of the memory bandwidth, about 3 terabytes per second. So existing systems are actually not very good at using existing memory bandwidth. They have low memory bandwidth to begin with, but they're also not very good at using it. We're also not extremely good at using it. Still, there's a lot more memory bandwidth that you can use, which means that the performance potential exists even more. And then there are also studies, you can say, oh, you're changing a lot in the system. Yes, absolutely. Some of the benefits are coming from higher bandwidth. Some of the benefits are coming from changing the programming model to take advantage of it. Some of the benefits are coming from prefetching, etc. In the end, it's a full system design to get all of the benefits of these 3D stacked memories by doing computation in them. But in the end, I think a good ballpark is half of the benefits are coming from increasing the bandwidth. A little bit more than half of the benefits are coming from a better programming model so that we can actually take advantage of the bandwidth and the prefetching mechanisms. Okay, so energy reduction is also commensurate. We get significant energy reduction, which is good, and the breakdown is in the paper. I should also say that this is published in 2015, right? There's a lot more work that built on this work to actually increase those numbers. I was fascinated. I think the latest work that I saw was in Micro 2021. There might be other works. Other people improved on this work. They basically did better balancing, load balancing, better graph partitioning, better interrupt handling, more customization to the graph workloads, etc. After all of that, I think the numbers are much closer to 100x in terms of energy reduction and 100x in terms of performance improvement. Now, think about those numbers a little bit. This is energy reduction and performance improvement 100x at the same time. So you're really improving the energy delay product by 100 times 100 if you actually do a very rough calculation, right? So that's actually fascinating. And we're not even doing analog computation here. This is pure logic near memory. Okay, so that was Tesseract. More recently, I'm not going to go through this, but this is actually a very fascinating paper. We collaborated with Torsten Hoffler's group at ETH. Machi, actually, he's a senior researcher. And we had this idea of using sets to represent graphs. And sets are very nice actually. So if you remember ambits, the previous block bitwise operations, one of the benefits is if you're doing set operations, like set intersection, set union, those are all AND or XOR operations. So you can actually do the block bitwise operations on bit vectors. So we wanted to actually represent graphs using bit vectors and then map this to processing using memory and processing near memory. So in this work we provide algorithms for major graph programs or graph algorithms. We basically revisit them and essentially express them using set-centric mechanisms. We design a set-centric ISA, so instruction set architecture is all set-based. And then this is communicated to either processing using memory and processing near memory. So we do both actually here and show significant benefits. So again, we don't have time for this, but this is an across the stack paper that shows, oh, if you actually express your algorithms in a manner that's really suitable for processing using memory or near memory, like parallel bit vectors, you can get a lot higher performance benefits. It takes time, but it's possible to do it. Now, I think the interesting thing is some people in the machine learning domain are looking at set-centric expressions of machine learning also, and I'd be interested in seeing where that ends up and whether they can actually get similar benefits as we have shown for graphs. Okay, enough about graphs. Any questions? Yes?
So, the first, can you go a couple of slides back on the scheme? That one. So, you have, let's say, NOMA-like.
Yes.
Like in traditional NOMAs, when you want to access the remote memory, you get to the hit cache. How does this system interact when one node tries to access memory from the other? So
you basically send a message.
Send a message. But
yeah.
Where does it send? So what's the path? So it goes through one processor?
It gets routed through the interconnect. Yes. So there's interconnect. That's why we have interconnect that's connecting these cores over here, and we explore different interconnects. We ended up with Dragonfly interconnect. Yes. But you send a message to update the node saying that here's the function that I want to use. Please update it with this input data. Yes.
Like explicitly programming the...
Exactly, yes. That's the downside of this mechanism, right? In the end, the programmer needs to do everything. So you can think of this like an early GPU, right? The early GPUs were like this, is completely explicitly programmed. But over time, this could actually become an easier to adopt programming model if you develop the stack on top of it. Yes?
So you are moving functions instead of moving data, but still you are moving something. So as far as I see it, regarding to the amount of data you are moving, it could be possible that the data that you are moving, which is an idea of a graph node, and usually it is for graph computation, is smaller than the footprint of the function that you are moving. Is the benefit in not moving the data in that you always know where the data is situated, or in the amount of data you're moving?
So I think it could be both, depending on what you're doing. And not all graph algorithms move just one small thing. There are different graph algorithms that do multiple things on multiple vertices, for example. So it could be both, but we also get benefits from parallelizing these accesses as well across different units. We can talk more about that.
Okay.
Yeah. But what you said is valid. There are some cases where we move more stuff, but later works optimize that also. That's how they got more. Okay. Okay, so let's move to some other things. So later we actually were very interested in looking at like commercializing some of these things, and I spent some time at Google in my previous sabbatical, and my student also spent some time at Google, and we actually analyzed can we actually get some benefits from computation near memory using in mobile devices. And this is what we did. I mentioned this already very quickly. Basically, clearly, energy consumption is very important in mobile devices. We examined these 4 workloads. I mentioned that. And we analyzed these workloads heavily, and we found out that more than 60% of the total system energy is spent on data moment. And then we went further. We wanted to understand what kind of functions cause these data moment, and we wanted to do the function offloading. We don't want to redesign the entire system like we did with Tesseract. We wanted to just identify simple functions and offload them to the memory side. And the observation is that there are some simple functions that you can offload relatively easily because they're responsible for most of the data moment. So you can implement these functions as small embedded low power cores, just like Tesseract, or you can actually have specialized accelerators that are designed in RTL, or you could have a reconfigurable engine in the logic layer of the memory, 3D stacked memory. And we found out that if you do this carefully, you get 2 to 3x performance and energy improvements, which is not bad. It's not 13x, but 2x is not a bad point to start with. So what are these functions? I'm not going to talk about everything, but for example, compression, decompression, that's used a lot in tab switching in Chrome browser is one. In machine learning, at the time we used TensorFlow, and we found out that a lot of the inference energy is spent on data movement, more than 50%, and more than 50% of that data movement comes from 2 simple functions, packing and unpacking of data, so that you can process that nicely, and quantizing of data. Essentially all models do that today. And if you think about these functions, these are relatively simple functions. They're like quantization is really chopping off some bits, but it's very data intensive, but the computation is very simple. I mean, it's a little bit more than chopping bits, but packing and unpacking is really reorganizing the data. And that's also computation is very simple over there. So if you offload this sort of computation, this is what you would get. We would actually, these are functions, function-based energy evaluation. For example, in Chrome browser, we offload compression and decompression to memory. In TensorFlow, I already mentioned that. In video playback, we offload motion estimation, which is a very heavy, intensive function in terms of data. And we see significant energy reductions, even if you offload it to a simple core, general purpose core. And if you actually offload to an accelerator, you get even more energy reduction. In more complicated functions, you see that you get even more energy reduction by doing acceleration as opposed to general purpose cores. That's energy, this is runtime. It turns out actually accelerators are much more important for runtime compared to energy in these particular cases. For example, compression and decompression don't gain a whole lot from energy, although they do gain a little bit, but they do gain a lot in terms of performance. But in the end, the takeaway is that you get between 2 to 2.5x improvement in terms of both performance and energy at the same time by offloading these important functions. Okay. So later, we continued working with Google. We spent some more time over there together with them, and we wanted to really understand, okay, machine learning accelerators are quite interesting. Are they really designed to treat these models carefully? And the answer is kind of no, together with Google folks. Maybe I'll quickly summarize. Basically, we examined many edge models that are used at Google. Unfortunately, these are not open source. They use this for commercial purposes, but we were able to analyze them. And we analyzed Google Edge TPU, which is a smaller version of the data center TPU that Google has. It's essentially a big systolic array. And we found out that it's essentially limited by memory. I'm going to show you more examples of this. And one of the main reasons it has a monolithic design. It's a compute-centric accelerator that's over-provisioned for computation, and it's wasting a lot of time waiting for data. No surprises here compared to what I said a couple of lectures ago. So in order to alleviate that, we made it a more heterogeneous accelerator. The idea is to have multiple different accelerators. One of them is compute-centric but smaller. 2 of them are data-centric, and they're catering for different types of data flows in the machine learning models. And in the end, we found out that we could improve both performance and energy by 3x, around 3x at the same time, while also reducing the hardware real estate. Meaning the existing Edge TPU, if you look at the hardware cost, you could design 3 accelerators that are much smaller in aggregate compared to the existing TPU, which is also fascinating to me. Okay, but of course the complexity is higher. Now we have 3 accelerators to deal with, right, as opposed to 1 accelerator. But you have much higher performance and energy efficiency. Let me go through this relatively quickly. Essentially, this is what we analyzed. 24 edge neural network models. Some of them are more intensive, like LSTMs and transducers. And this is essentially, this is the first insight we generated was there's a huge variation in terms of layer characteristics across the models. These are for CNNs and LSTMs, as you can see. On the x-axis, you have parameter footprint, how large are your parameters. On the y-axis, you have the arithmetic intensity, flops per byte. And you can see that there's a huge variation. Both of these are logarithmic scales. LSTMs end up over here, which means that they're probably an extremely good fit for processing near memory. Whereas some of the CNNs have very high arithmetic intensity. They are probably a good fit for compute-centric accelerators. So it kind of doesn't make sense to design a single accelerator to cater for all of these. And then the second insight is even within a model, different layers, different neural network layers, exhibit different characteristics. This is different layers, numbered, and this is multiply and accumulate operations. You can see that there's a huge variation. And this is layers and arithmetic intensity. Again, there's a huge variation, and these are different convolutional neural networks. Okay, so this is the idea. As opposed to designing a single monolithic accelerator that's over-provisioned, we design 3 different types of accelerators. It doesn't have to be 3. In this particular prototype, we had 3 that are catering for different families of layers coming from models. And then the important thing is you need to design a scheduler that identifies the layers and says, okay, this layer is going to execute here, this layer is going to execute here, this layer is going to execute here. I'm not going to go through the design of the different accelerators, but the first accelerator is a compute-centric one. It's essentially similar to this one, but it's much smaller because it doesn't need to deal with the memory-bound parts, memory-bound layers. The other 2 accelerators are under 3D stacked DRAM in the logic layer, and one of them is smaller, the other one's bigger, to deal with different types of, let's say, data-centric or data-intensive layers. And the data flows are also customized. Okay, how do you identify layer families? Essentially, we do some profiling, and we look at arithmetic intensity and parameter footprint and the number of multiply and accumulate operations. And these are the families we came up with, essentially using clustering. And different families get routed or scheduled onto different type of processors or accelerators. Again, there's a lot more detail over here, but I'm kind of giving you the higher level insight. By looking at several simple metrics like arithmetic intensity, number of multiply and accumulates, and parameter footprint, which you could profile over time also, you could actually identify where you should execute something. And these are the results that we get. This is energy reduction. I kind of showed you this picture yesterday. So if you look at, these are the LSTMs and transducers, which are much more intensive. And these are the CNNs and RCNNs. And if you look at this, this is the baseline. I'm going to pick one of these over here. This is baseline. This is what happens if you add high bandwidth memory to the baseline. At the time, TPUs didn't have high bandwidth memory. Now they have high bandwidth memory. So you get some energy reduction, but not a whole lot. And this is what happens if you actually employ what we propose. So you get a lot of energy reduction, as you can see. And you can see that the baseline is really dominated, baseline plus HBM-based baseline. They're both dominated by off-chip interconnect and DRAM in terms of energy. We're still dominated by accessing DRAM in terms of energy, but we're much better in terms of absolute energy numbers. So basically, you can get energy reduction across the board, and it's significant. It's about 3x. Performance is a different issue. So if you look at this, this is the baseline. This is the throughput of executing many models. And throughput increases significantly if you actually use high bandwidth memory. So high bandwidth memory increases throughput, but it's not affecting energy as much, as you can see. This is expected also, if you know about memory. We improve throughput even more compared to high bandwidth memory, but not as much as we improve energy. So in the end, throughput still improves, especially in some of these models, but compared to high bandwidth memory, the improvements are smaller. So high bandwidth memory tends to be very good for performance, not so good for energy.
So in this
Yes.
So in this one, we only use the TPU without the GPU?
So in this case, yes, we're only using TPU. We're not looking at GPU, yes. But I believe GPUs will have similar deficiencies, let's say. Okay. Any questions? Okay, I'll end soon. We start a bit later. Okay, so let me talk about genomic data filtering. I'm going to move to storage right now. So if you look at genomics, there's huge amounts of data that's manipulated, that's moved, and the operations that you do can be relatively simple. Let me give you the perspective of the problem. I think this may be the last work we examine. Let's see. In this what you do in genomics is, in sequence analysis at least, you have a reference genome, and you get some sample, and the sample provides you some reads, essentially chopped pieces of your DNA, of a DNA that you sampled, and you compare it to a reference genome, one or many reference genomes. In this case, we're looking at one reference genome. In our recent ISCA paper, we have actually many reference genomes. So what happens is you need to move a lot of data from the storage system all the way to computation units. And then you need to do the alignment. This is a process called alignment to compare. It has a lot of computation overhead, and there's a lot of data movement overhead. Now, people have optimized the computation overhead a lot. In this case, I'm treating main memory also as part of the computation unit, as you can see. People have had a lot of heuristics, accelerators, filters, both at the software and hardware levels. These are all targeted toward computation overhead. They reduce the computation overhead. Once you reduce the computation overhead, data movement overhead becomes an even bigger bottleneck. This is basically Amdahl's law, right? If you fix one of the overheads, the other overhead becomes dominating. So we wanted to tackle this data movement overhead, especially from the storage system. And the idea over here is filter some of these sequences or reads that do not require alignment quickly over here, such that very little amount of data is moved to the computation unit that's tasked with doing much more sophisticated jobs. To do the hard things for computation over here, do the simple things for computation over here. You can think about it that way. And this way you can filter a lot of the reads, only a small amount goes to the computation unit. So what can you filter? Now you become application specific over here. That's why I think whenever you talk about processing near memory, you should think applications. What can I do in this application to accelerate this application? So what can you filter? Some things are a lot easier to filter. For example, you have a part of the genome, you have a sequence that you sequenced. You can compare easily whether those two match. This is basically a simple XOR tree, right? It's a comparator. And that's very simple to implement over here. If something doesn't match with a wild difference, that's also relatively easy to detect. Right? You can basically take this part of the sequence and this part of the genome, and you take a Hamming distance. If the Hamming distance is huge, then probably these are not going to match. In fact, we have a lot of works that showed that in the past. So you can actually do these computations relatively simply on the storage system without adding a lot of logic. And we do that, and we reduce the data movement overhead. And again, without going through a lot of details over here, we see significant speed up and energy reductions at low cost. Speed up and energy reductions varies depending on your input set. It depends on what fraction of your reads are exactly matching the reference genome, what fraction of your reads are not matching the reference genome. If you're not able to filter effectively, then your performance energy benefits are not high, of course. But in going forward, we're actually looking at how to actually expand this. As I said, this was published in ASPOS 2022. I don't have the slides for the ISCA this year. Actually, I do have the slides, but I didn't put them over here. But these data set sizes are actually growing in genomics because you're not operating on a single genome. There are some genomic applications where you sample. Okay, I sample something from this ground over here, right? I put it through my sequencer. And I want to understand what's there, right? If you want to understand what's there, you compare it to a huge set of databases with different reference genomes. It could be any type of virus, it could be any type of human or animal, whatever you get over there. So it's actually a huge comparison. So the data set sizes that you have are way beyond what we can fit in main memory, and in many cases way beyond what we can fit in a single storage device. So that's why I think this is a very data intensive process, and increasingly these things are happening. There are actually very interesting studies in genomics. People, for example, sampled exactly what I said. People have done it in the New York metro subsystem, and they found very interesting results. What kind of bacteria is lurking in the New York metro? Don't touch a lot of things in the New York metro. Basically, these things are actually real, and they have real applications. In some cases, they have real applications in critically ill patients, for example. You can actually have a very quick way of what kind of drug you should use. In some cases, it's important for understanding what kind of outbreak may happen next. Okay, so I think we're out of time. Is that correct? Yes. Okay, I won't keep you longer, but tomorrow we're going to start with the remaining part of memory-centric systems. We're going to talk a little bit more about near memory computing, and then we're going to talk about some real systems, and then we're going to conclude, and then we're going to switch to memory robustness, which is another fascinating area, and we'll talk about how people are actually doing near memory computation to fix memory robustness issues. And I'll see you around.